All right, Honors Math 3, let's finish off this chapter 14 if we could. We finished talking about derivatives, some shortcuts, some calculator work, so have your graphing calculator handy. Some of you turned in all of the 14.4 homework. I'm a little concerned that you didn't know how to do some of it, that you did. So you might have to spend a little time redoing now that we see some things today. Alrighty, I'm going to use the difference quotient, remember what that is, to find a function for the derivative. So we're asked to find this. F prime of x is equal to some formula for the derivative. Okay, what was the difference quotient? The difference quotient was a way to find f prime of x as a limit as h approaches 0, the difference between x values of f of x plus h minus f of x all over h, as h gets smaller and smaller and smaller. Let's rewrite that. That's the limit as h approaches 0 of what is f of x plus h. I'm going to plug that in wherever I see an x into f of x. That's 2 times x plus h squared plus x plus h minus the function itself, there it is, which is 2x squared plus x all over h. Sometimes I do this work right in here. Sometimes I do that little work off to the side, so it's up to you. F of x plus h. Okay, so multiply that out in either way. I'm going to pause. When I expand f of x plus h, I got this. So I substitute that into that numerator. I'm going to distribute this negative, minus 2x squared minus x. Okay, nice polynomial function, so things will always cancel. Those are gone. Those are gone. And this becomes the limit as h approaches 0. Notice what's left in the numerator, 4xh plus 2h squared plus h, all divided by h. I still can't plug in h equals 0 because my denominator is undefined, but I can divide everything in that numerator by h, so I can simplify this to the limit as h approaches 0 of, divide everything through by h, 4x plus 2h plus h divided by h, which is 1. As h approaches 0, this term becomes 0, it's gone, and I am left with 4x plus 1. Voila! And I just got a formula to find the derivative of this function for any x value. Alrighty, so that's finding a function for the derivative using the difference quotient. Haha! Now we're ready for a little shortcut to find a derivative. I don't know if you can see how we can quickly go from here to here for a polynomial function only. We have a shortcut to go from here to here, and we're going to look at that for a moment. Okay, you ready? This is life-changing. Difference quotient you need to know for any function, but for a polynomial function, we get this cool shortcut. This is the same function, 2x squared plus x, and I'm going to find the formula for that derivative. Watch this. I take exponent times coefficient, 2 times 2 is 4, x to the, knock that degree down by 1, 2 minus 1 is 1, plus exponent times coefficient, 1 times 1 is 1, x to the, knock that down by a degree, 1 minus 1, which is 0. That looks terrible. So that implies that f prime of x is equal to, that's just 4x to the first, plus, you would not write that coefficient, x to the 0 power, but x to the 0 power is 1. And 1 times 1 is 1. Wah-ha! And there is that function for the derivative. Yes, let's try that one more time. And I'll write a little note of how we use this shortcut, but watch this. I'm going to find a function for the derivative of this polynomial function. Only works for polynomials. Watch this. Multiply exponent times coefficient, knock that degree down by 1, plus exponent times coefficient, 12, knock that degree down by 1. This is, what is this? X to the 0 power, actually it's not there. When I multiply exponent times coefficient, 0 times 10 is 0, and that's just gone. So the function for the derivative is negative 20x cubed plus 12x. Ha! You can always use the difference quotient. You could have used the difference quotient to find this, but there is a cute little shortcut for a polynomial function. Again, some of you did your homework before we knew this shortcut. You might want to look at that, what was it, like 21, 25, 29, which you did with a difference quotient the other day. Now you're going to try it again with that shortcut. So you might want to try those again today, just so they make sense. All right, so now as long as these are polynomial functions, I'm going to use that shortcut to find the derivative at 0, 0, and find the derivative at x equals negative 1. I'm going to pause for a moment to let you find this. What is f prime of x? Find a formula for the derivative. Find a formula for the derivative with that cute shortcut. Here's my little hint for you if you want to remember that or jot that down. But this should be the formula for your derivative. 3 times 2 is 6, x to the first, minus 1 times 1, which is 1, x to the 0. That's the formula for my derivative. So f prime I want at x equals 0 of 0 is 0 minus 1, which is negative 1. And the derivative at x equals 0 is negative 1, the slope of the tangent line. Use your shortcut to find a function for the derivative. 3 times 1 is 3, x squared. 1 times 4 is 4, x to the 0. So I'm going to write that as f prime of x is equal to 3x squared plus 4. And now I want f prime of negative 1, which is, what's negative 1 squared is 1 times 3, 3 plus 4, which is 7. That's the slope of the tangent line at x equals negative 1. Alrighty? Alright, this is a great shortcut. You can always use our difference quotient. This is a shortcut for polynomial functions to find a formula for the derivative. Sometimes I cannot use these algebraic methods. This is a terrible function. Actually, next year you will be able to find the derivative for that function. But for our purposes, let's figure out how we can use our graphing calculator when a function gets more complicated. Okay, so pause and grab your graphing calculator. Find the derivative of this function, the slope of the tangent line at x equals 8. Go to the Math menu, choose option 8, should look like this, and derive. It's called a numeric derivative. Okay, hit that on your home screen, and let's fill in the blanks that are there. This is the derivative with respect to x, you have to fill that in, of, your calculator is asking you for a function. So now I'm going to plug in this rational function. In the numerator, use parentheses, negative x cubed plus x. In the denominator, x squared plus 5x plus 7, use parentheses, and calculate that derivative at x equals 8. Hit enter. You see a decimal approximation, so you just found that f prime of 8 is approximately, what did your calculator give you? Let's round to 3 decimal places, negative 0.859. If you did not get that, try that little sequence of steps again, but we're going to try that one more time as I turn the page. Okay, let's use our calculators. My function is f of x equals e to the negative x times sine of x. And we're going to find the derivative at x equals 2. Okay, so math 8. Find the derivative with respect to x of the function e to the negative x sine of x. And let's evaluate that derivative at x equals 2. Your calculator gives you a decimal approximation. We're going to round to 3 decimal places, and I get negative 0.179. And that's the slope of the tangent line to that curve at x equals 2, or whatever number you want to find the derivative of. Alrighty? Let's see. Again, next year you will be able to find a formula for that derivative. We're just not there yet. We have more to learn. All right, let's continue on. I kind of started a little review because next week we're going to review for our test on Tuesday and have a Chapter 14 test on Thursday. So let's start reviewing what we've seen. The surface area of a sphere. Anyone know how to find the surface area of a sphere? Surface area of a sphere is calculated by 4 pi r squared. That's our formula for surface area of a sphere. Can you find the instantaneous rate of change of the surface area when the radius is 3, what are we in feet? When the radius is 3 feet, what's the instantaneous rate of change of the surface area? So imagine finding a surface area of a sphere and the radius keeps increasing, 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 increasing. If the radius is increasing, the surface area is increasing. At what rate when the radius is 3 feet? Okay, let me pause so you can think for a moment. Okay, we have to start thinking about what we would do here. Find the instantaneous rate of change. That means the slope of a tangent line. How do you find the slope of a tangent line? Either it's the limit as the radius approaches 3 of the slope, change in y, s of r minus s of 3, change in r, as the radius approaches 3. And you can calculate that limit. Or, I don't know if you recognize that this function, s of r equals 4 pi r squared, is a polynomial function. If it's a polynomial function, then I can use my cute shortcut, which I will. That implies that s prime of r is equal to, here's my variable, pi is just a number, a coefficient, multiply exponent times coefficient, that's 8 pi, and knock that exponent down by 1, r. That implies that s prime of 3 is 8 times pi times 3, which is 24 pi. Okay, what would this be? That's the surface area. What are units for surface area? Units for surface area are feet squared. What would this be? Units for radius is feet. Okay, there's my answer, but I'm going to state this. I'm going to state my solution. Okay, and I will answer the question that was asked. So the surface area of the sphere is changing at a rate of 24 pi feet squared per foot when the radius is 3 feet. Alrighty, as we continue starting to review this chapter, where is this function continuous? Try to remember when a function is continuous. And all of these are nice functions, quadratic, linear, linear, so they're continuous everywhere except possibly at those boundary points where things change in that piecewise function. So specifically, I'm going to check the boundary points and see if that function is continuous at x equals 0 and at x equals 2. Okay, so first, I'm going to check at x equals 0. How do we decide if a function is continuous? I ask myself, is f of 0 equal to the limit as x approaches 0 of that function? Pause and think about how you would check that. Okay, do you remember checking for continuity is a three-part process? First of all, I check the function value at x equals 0, which using this first piece is 0 squared, which is 0. Then, to check this, what is the value of the limit as x approaches 0? I find the value as x approaches 0 from the left. Again, using that first piece is 0 squared, which is 0, so all looks good. Then find the limit as x approaches 0 from the right of that function. That would be in the second piece, which is 0 plus 1, which is 1. Alrighty, and that fails continuity at x equals 0. Okay, since from the left and right of 0, my function values are approaching two different things, that limit as x approaches 0 does not exist. So since f of 0 is 0, as x approaches 0, that limit does not exist. F is not continuous at x equals 0. Now I'm going to do the same thing for that other boundary point. Check at x equals 2, is f of 2 equal to the limit? Take a moment and check that. Here's my work. Function value, limit from the left, limit to the right, Since they're all the same, I'm continuous at x equals 2, so f is continuous for all